Alright, let's continue. Let me open the table of content first. Okay, we are still on chapter 23 here, complete virtual memory system, and we are still on section 23.2, the Linux virtual memory system. Let me open that. Okay, let's check from the bottom. We need to take a look at this, but memory mapping, but I'm still not sure what is memory map file yet. Okay, now let's continue this. Security and buffer overflow. Probably the biggest difference between modern virtual memory system, Linux, Solaris, and one of the BSD variants, and ancient one like VAX/VMS, is the emphasis on security in the modern era. Protection has always been a serious concern for operating system, but with machines more interconnected than ever, it is no surprise that developers have implemented a variety of defensive countermeasures to hold those wily hackers from gaining control of system. One major threat is found in buffer overflow attacks, which can be used against normal user program and even the kernel itself. Okay, let me read the footnote first, I guess. See this URL for some details and link about this topic, including a reference to the famous article by the security hacker Elias Levy, known as Alep1. Okay. The idea of this attack is to find a bug in the target system which let the attacker inject arbitrary data into the target's address space. Such vulnerabilities sometimes arise because the developer assumes, erroneously, that an input will not be overly long and thus trustingly copies the input into a buffer. Because the input is in fact too long, it overflows the buffer, thus overwriting memory of the target. Is in fact too long, it overflows the buffer, thus overwriting memory of the target. Code as innocent as the below can be the source of the problem. This one, some function, right? Using strcpy, okay. Oops, unbound copy, right? I mean, if the string is more than 100 character, we got buffer overflow, something like that, with strcpy. In many cases, such an overflow is not catastrophic. For example, bad input innocently given to a user program or even the operating system will probably cause it to crash, but no worse. However, malicious programmers can carefully craft the input that overflow the buffer so as to inject their own code into the target system. To the target system, essentially allowing them to take it over and do their own bidding. If successful, you found a network-connected user program, attackers can run arbitrary computation or even run out cycles on the compromised system. Okay, if successful, you found a network-connected user program, attackers can run arbitrary computation or even run out cycles on the compromised system. If successful, you found the operating system itself, the attack can access even more resources and is a form of what is called privilege escalation. That is user code gaining kernel access rights. You can guess these are all bad things, okay? The first and most simple defense against buffer overflow is to prevent execution of any code found within certain regions of an address space, for example within the stack. Okay, yeah, in case you are wondering, if the user code gaining kernel access, it means the code or the program can do everything, I guess. So that can be bad, right? Okay. The most simple defense against buffer overflow is to prevent execution of any code found within certain regions of an address space, for example within stack. The NX bit, okay, for no execute, introduced by AMD into their version of x86. A similar XD bit is now available on Intel. Okay. Is one such defense? It just prevents execution from any patch which has this bit set. Execution from any page which has this bit set in its corresponding page table entry. The approach prevents code injection, prevent code injected by an attacker into the target stack from being executed, and thus mitigates the problem. However, clever attackers are, well, clever, and even when injected code cannot be added explicitly by the attacker, arbitrary code sequence can be executed by malicious code. The idea is known in its most general form as return-oriented programming. Oh, interesting. Yeah, I didn't know about return-oriented programming. Okay, and really it is quite brilliant. Okay, the observation behind ROP or return-oriented programming is that there are lots of bits of code or gadget in return-oriented programming terminology. Oh, gadget, okay. Lot of bits of gadget, maybe something like that. Within any program's address space, especially C program that links with the voluminous library. Thus, an attacker can overwrite the stack such that the return address in the currently executing function point to a desired malicious instruction or series of instruction followed by a return instruction by stringing together a large number of gadgets that is ensuring its return jump to the next gadget. The attacker can execute arbitrary code. Amazing. The defense against return-oriented programming. Against return-oriented programming, including its earlier form, the return to Libc attack. Its earlier form called the return to Libc attack. Linux and other systems add another defense known as address-space layout randomization, ASLR here, address-space layout randomization. Instead of placing code stacked in the heap at fixed location within the virtual address space, the operating system randomized their placement, thus making it quite challenging to craft the intricate code sequence required to implement this class of attack. Most attacks on vulnerable user program will thus cause crashes, but not be able to gain control of the running program. Interestingly, you can observe this randomness in practice rather easily. Is a piece of code that demonstrates it on modern Linux system. This one. This code just prints out the virtual address of a variable on the stack. This one, the stack variable here. And well, the address, I assume, will change every time we run this instruction because of the ASLR, address space layout randomization. In other non-ASLR system, this value would be the same each time. But as you can see below, the value changes with each run. This is the first run, right? This is the second run. This is the third run. And it's different each time we run the executable or the program. ASLR is such a useful defense for user-level program that it has also been incorporated into the kernel in a feature unimaginatively called kernel address space layout randomization. Unimaginatively, okay. KASLR. Okay. Incorporate into the kernel. Okay. However, it turns out the kernel may have even bigger problem to handle, as we discuss next. Other security problem, Meltdown Inspector. Okay, as we read these words, August 2018, the world of system security has been turned upside down by two new and related attacks. The first called Meltdown and the second Spectre. They were discovered at about the same time by 4 different groups of researchers or engineers and have led to deep questioning of the fundamental protection offered by computer hardware and the operating system above. See SpectreAttack.com for papers describing its attack in detail. Oh, there's a URL here. Okay. Spectre is considered the more problematic of the two. The general weakness exploited in each of these attacks is that the CPUs found in modern systems perform a sort of crazy behind-the-scenes tricks to improve performance. One class of technique that lies at the core of the problem is called speculative execution, in which the CPU guesses which instruction will soon be executed in the future and start executing them ahead of time. If the guesses are correct, the program runs faster. If not, the CPU undoes their effect on architectural state, for example register, and tries again, this time going down the right path. Oh, speculative execution. Guess which instruction will soon be executed in the future and start executing them ahead of time. Oh, okay, interesting. The problem with speculation is that it tends to leave trace of its execution in various parts of the system, such as processor gates, brains, predictors, etc. And thus the problem, as the author of the attack show, such state can make vulnerable the content of memory. Even memory that we thought was protected by the memory management unit. One avenue to increasing kernel protection was thus to remove as much of the kernel address space from each user process and instead have a separate kernel page table for most kernel data called kernel page table isolation or KPTI. Okay. Increasing kernel protection, remove as much of the kernel address space from its user process and instead have a separate kernel page table for most kernel data. Okay, thus, instead of mapping the kernel's code and data structure into each process, only the bare minimum is kept therein. When switching into the kernel, then a switch to the kernel page table is now needed. Doing so improves security and avoids some attack vectors, but at a cost. This is the trade-off. Performance, right? Switching page table is costly. The cost of security. Yeah, the cost of security, convenience, and performance. Right. Unfortunately, KPTI or kernel page table isolation doesn't solve all of the security problems laid out above, just some of them. And simple solution, such as turning off speculation would make little sense because system would run thousands of times slower. Thus, it is an interesting time to be alive if system security is your thing. Okay. To truly understand these attacks, you will likely have to learn a lot more first. Begin by understanding modern computer architecture as found in advanced book on the topic, focusing on speculation. Okay. Understanding modern computer architecture as found in advanced book on the topic, focusing on speculation and all the mechanism needed to implement it. Definitely read about the Meltdown and Spectre attack at the website mentioned above. They actually also include a useful primer on speculation, so perhaps are not a bad place to start and study the operating system for further vulnerabilities. Who knows what problems remain? Are not a bad place to start. Primer on speculation. Interesting. And then the summary. You have now seen a top to bottom review of two virtual memory system. Top to bottom review of the virtual memory system. Hopefully, most of the details were easy to follow, as you should have already had a good understanding of the basic mechanism and policies. More details on VAX/VMS is available in the excellent and short paper by Levy and Lipman. We encourage you to read it, as it is a great way to see what the source material behind this chapter is like. You have also learned a bit about Linux. While a large and complex system, it inherits many good ideas from the past, many of which we have not had room to discuss in detail. For example, Linux performs lazy copy on write, copying of page upon fork, thus lowering overhead by avoiding unnecessary copying. Linux also demands zero page, usually memory mapping of the /dev/0 device, and has a background swap daemon swapd that swap page to disk to reduce memory pressure. Indeed, the virtual memory is filled with good ideas taken from the past and also includes many of its own innovation. To learn more, check out this reasonable but less outdated books. Okay, we encourage you to read them on your own, as we can only provide them merely drop from what is an ocean of complexity. An ocean of complexity. But you've got to start somewhere, right? What is any ocean but a multitude of drops? Oh, okay. This is the reference. The first reference is efficient virtual memory for big memory server. A recent work showing that translation look aside buffer matter consuming 10% of cycle for large memory workload. The solution: one massive segment to hold large data sets. We go backward so that we can go forward. Alright, then next, a batch time sharing system for the BDP-10, an early time sharing operating system where a number of good ideas came from. Okay, copy on write was just one of those. Also an inspiration for other aspects of modern system, including process management, virtual memory, and file system. Okay, converting a swap-based system to the patching in an architecture lacking patch reference speed. Alright, how to exploit existing protection machinery to emulate reference speed. From a group at Berkeley working on their own version of Unix, the Berkeley System Distribution (BSD), the group was influential in the development of virtual memory, file system, and networking. Okay, understanding the Linux kernel, one of the many books you can find on Linux, which are out of date, but still worthwhile. Okay, The Innovator's Dilemma. Oh, a fantastic book about the disk drive industry and how new innovation disrupt existing ones. A good read for business major and computer scientists alike. Provide insight on how large and successful companies completely fail. Oh, large and successful companies completely fail. Okay, inside Windows NT, the book about Windows NT that explains the system top to bottom in more detail than you might like, but seriously, a pretty good book. Okay, understanding the Linux Virtual Memory Manager, an in-depth look at Linux Virtual Memory, but alas a little out of date. KASLR is dead. Long live KASLR. What? Isn't this the same? Available in this URL. Excellent info on KSLR. The kernel address space layout randomization and kernel page table isolation and beyond. Okay. To queue a low overhead high performance buffer management replacement algorithm, a simple but effective approach to building patch replacement. Okay, virtual memory management in the VAX/VMS operating system. Read the original source of most of this material. Particularly important if you wish to go to graduate school, where all you do is read papers, work, read some more papers, work more, eventually write a paper, and then work some more. Okay. Basically either read paper or work. Okay. The graduate student life, I guess. Cloud Atlas. It's hard to pick a favorite book. There are too many. Each is great in its own unique way, but it would be hard for this author not to pick Cloud Atlas. A fantastic, sprawling epic about the human condition, from where the last quote of this chapter is lifted. If you are smart, and we think you are, you should stop reading obscure commentary in the reference and instead read Cloud Atlas. You'll thank us later. Okay. Virtual memory and Linux. Okay. A useful set of slides which give an overview of the Linux virtual memory. Okay. Segmented first in first out batch replacement. A short paper that shows for some workloads. Segmented first in first out can approach the performance of least recently use. Okay. The geometry of innocent flesh on the bone. A generalization of return to lip. Dr. Beth Garner said in Basic Instinct, "She is crazy, she is brilliant." We might say the same about ROP, return-oriented programming. Okay. On the effectiveness of address-based randomization. Okay, wait a minute. Okay, a description of the return to libc attack and its limit. Start reading, but be wary. The rabbit hole of system security is deep. Okay. Alright. That is for chapter 23. And let's read the summary. Summary dialog on memory virtualization. Let me open this. Alright, summary dialog on memory virtualization. Student groups. Wow, that was a lot of material. Yes. The professor, yes, and well, how am I supposed to remember it all? For the exam. Goodness. I hope that's not why you are trying to remember it. Why should I then? Come on. I thought you knew better. You are trying to learn something here, so that when you go off into the world, you will understand how systems actually work. Can you give an example? Sure. One time back in graduate school, my friends and I were measuring how long memory access took. And once in a while, the numbers were way higher than we expected. We thought all the data was fitting nicely into the second level hardware case, you see, and thus should have been really fast to access. Alright. We couldn't figure out what was going on. So what do you do in such a case? Easy. Ask a professor. Okay. So we went and asked one of our professor who looked at the graph we had produced and simply said, TLP. Aha. Of course, TLP miss. Why didn't we think of that? Having a good model of how virtual memory works help diagnose a sort of interesting performance problem. I think I see. I'm trying to build this mental model of how things work so that when I'm out there working on my own, I won't be surprised when a system doesn't quite behave as expected. I should even be able to anticipate how the system will work just by thinking about it. I should even be able to anticipate how the system will work just by thinking about it. Exactly. So what have you learned? What's in your mental model of how virtual memory works? Well, I think I now have a pretty good idea of what happens when memory is referenced by a process which, as we have said many times, happens on its instruction fetch as well as explicit loads and store. Okay. What happens when memory is referenced by a process which, as we have said many times, happen on its instruction fetch as well as explicit loads and store? Sounds good. Tell me more. Well, one thing I'll always remember is that the address we see in a user program, written in C for example. What other language is there? Yes, I know you like C. So do I. Anyhow, as I was saying, I really know that addresses that we can observe within a program are virtual address, that I, as a programmer, am just given this illusion of where data and code are in memory. I used to think it was cool that I could print the address of a pointer, but now I find it frustrating. It's just a virtual address. I can see the real physical address where the data live. Nope, the operating system definitely hides that from you. What else? Well, I think the TLB, or translation look aside buffer, is a really key piece, providing the system with a small hardware case of address translation. Page tables are usually quite large and hence live in big and slow memory. Without that TLB, the translation look aside buffer, program would generally run a great deal more slowly. Seems like the translation look-aside buffer truly makes virtualizing memory possible. I couldn't imagine building a system without one, and I shudder at the thought of a program with a working set that exceeds the coverage of the translation look-aside buffer. With all those TLB miss or the translation look-aside buffer miss, it would be hard to watch. Yes, cover the eyes of the children. Beyond the translation look-aside buffer, what did you learn? I also now understand that the page table is one of those data structure you need to know about. It's just a data structure though, and that means almost any structure could be used. We start with simple structure like array, also known as linear page table, and advance all the way up to multi-level tables, which look like trees, and even crazier things like pageable page table in kernel virtual memory, all to save a little space in memory. Indeed. And here's one more important thing. I learned that the address translation structure need to be flexible enough to support what programmers want to do with their address space. Structures like the multi-level table are perfect in this sense. They only create table space when the user needs a portion of the address space, and thus there is little waste. Earlier attempt, like the simple base and bound register, just weren't flexible enough. The structure need to match what users expect and want out of their virtual memory system. The structure need to match what users expect and want out of their virtual memory system. Right. Previously we learned about base and bound register. I think in chapter... where is it? Maybe in the early chapter. Where is it? Is it in the segmentation? Oh, maybe this one. Before the segmentation. I mean the segmentation, what is it called? Rather than the entire address space, we have base and bound for different segments. Maybe something like that. Yeah, maybe in this chapter 15, if you want to revisit that. Okay, that is a nice perspective, right? What about all of the stuff we learned about swiping to this? Well, it's certainly fun to study and good to know how page replacement works. Some of the basic qualities are kind of obvious, like least recently used. For example, but building a real virtual memory system seems more interesting, like we saw in the VMS case study on this. Where is it? This one, I guess. VAX VMS virtual memory. But somehow I found the mechanism more interesting and the policies less so. Oh, why is that? Well, as you said, In the end, the best solution to policy problem is simple. Buy more memory. I think it was mentioned in chapter 22, I guess, when we are talking about batch replacement policy. And yeah, the best solution is buy more memory. But the mechanism you need to understand to know how stuff really works. Speaking of which, yes, well, my machine is running a little slowly these days, and memory certainly doesn't cost that much. Okay, back then at least. Oh, fine. Here's a few bucks. Okay. Go and get yourself some DRAM. Chips. Thanks, Professor. I'll never swap to this again. Or if I do, at least I know what's actually going on. Okay, what a nice professor, right? Alright. Okay, we have done with the first piece, I guess, the virtualization piece. The next one, continuing to the concurrency piece. And you know what? Let's continue about concurrency, or maybe start on the concurrency piece on the next session. So that's it for now. Thank you for watching and see you next time. Bye bye.